Then after having discussed what a system means and what a model means and how these analysis of these various models are facilitated by a common body of tools coming under the name system analysis, system theory. Let us now look up, see how we represent a system. Very often we are interested in finding out the response of a system under the influence of a particular input. We are not so much bothered about the various variables, the various signals internal to the system. In this event, we represent a system as a black box. And the various inputs that are given to the system are represented in this manner, maybe call this x1, x2 right up to xm. And under the influence of these various inputs, there are certain responses in the system which we are interested in. These are called the outputs or responses. Similarly, the inputs are called excitations also. Other name is excitations. So we may say the system responds under the influence of an excitation, or the system gives an output under the influence of an input. And there may be n such responses we are interested in. So in this particular system, we possibly have m inputs and n outputs, and then a representation like this is referred to as a multiple input, multiple output system. So let us consider an electrical network. You have several sources, voltages and currents, and we would like, these are the various inputs to the electrical network, current source and voltage sources. We are interested in finding out the voltage and currents at different points. We are interested in finding out all those responses, so we can model this as a multiple input, multiple output system. On the other hand, very often we might be interested in finding out the influence of one particular input, and we would like to find out the response at a particular location. Then we have x of t may be the input signal, y of t is the output signal. So we may call this again as input or excitation. And this can be called the response, output, and this will be called single input, single output system. For the class of systems which we will talk about later, linear time invariant systems, if we have a complete knowledge of how a system behaves with a single input and a single output and a particular output, then we can use that information to get a particular response when a variety of inputs simultaneously occur by the principle of superposition, and this is something which we can always do for the particular class of systems that we are talking about. So our concentration may be for most of the time on a single input, single output system, but that does not in any case take away from the generality of the tools that we employ. To simplify this notation, this is a block diagram representation of a system. I mentioned this as a black box because we are not particularly interested in what is inside. Therefore, we can assume this to have two terminals where the input is fed and two terminals when its output is fed, taking the electrical circuit as an example. And this whole concept of a particular input giving rise to an output can also be very succinctly and compactly indicated as xt and ROYT. That means in a particular system, once we know what the system is, we can say then the system input xt gives rise to output yt. This is the excitation, this is the response. So very often we use this type of notation when we have to deal with a particular system and we would like to have a variety of inputs, and what are the outputs that you get, we use this kind of compact representation to indicate the input output relations of a system. As I said, systems are quite diverse in nature, and naturally their properties also will be diverse in nature, but we would like to classify the systems depending upon the particular property or characteristic that we have in mind. So let us now talk about classification of systems. One can classify system as either a static system or a dynamic system. A static system is one in which the output depends upon the input at that time and on nothing else. It does not depend upon what happened in the past. The past history of the system is immaterial. So if you give a particular input, the output is dictated by that input. Nothing else is required. Take for example an electrical resistor. The current in that resistor depends only on the voltage at that particular point of time. Not that how that voltage has come about, nor about its rate of change, etc., but it depends just on the voltage at a particular time dictates the current in that resistor. So if a resistive network is there, a one port resistive network, then if the input voltage is given, the current is immediately deduced by the magnitude of the voltage at that particular point of time. So static networks are also sometimes called memoryless networks or memoryless systems. Example, a resistive network. Whereas a dynamic network, it is not enough if you know the values of the instantaneous values of the inputs at that time. You should know something more. You should know perhaps a kind of summary of what happened in the past, in the form of, suppose let us take an RLC network for example. If you want to know the response of an RLC network to a impressed excitation, the driving force, you should also know what is the initial charge in the capacitor, what is the initial current in the inductor. And this is what has come about because the past history of the network, whatever excitations it has been applied with and whatever remnants it has left in the system. So in a dynamic system, the response depends not only on the instantaneous values of the input, but perhaps on the derivatives of the input and also the integrals of the input quantities and so on. So it doesn't merely depend upon the instantaneous values, the rate of change of the inputs, the integrals values of the inputs, the past history of the input as summarized by the initial conditions are all important in the case of dynamic systems. Example, an RLC network. So if you are having an RLC network with given excitation functions, it's not enough to know the complete solution problem. You should also know the initial currents in the inductors and the initial charges in the capacitors. So it turns out that when you want to describe a static system, the equations governing the performance turns out to be purely algebraic in character. Whereas, since in a dynamic situation you need to take stock of the derivatives, the time variation of the various quantities, we have integral differential equations, or an integral differential equation can always be reduced to a differential equation, but in general we can say integral differential equation. So you have on one hand some differential equations, and also you have differential derivatives as well as integrations of the integrals of the various quantities, and so in general it will be integral differential equations that govern the performance of a dynamic system. A second method of classification of systems is to categorize them as a continuous time system or a discrete time system. Alternately discrete time. In a continuous time system, the input-output relations are defined for every instant of time on a continuous basis. In other words, we are interested, or we can calculate in principle, the variables at every single point of time on the time axis on a continuous basis. Whereas, in a discrete time system, you have these input-output relations. Discrete time system, you would have an input-output relation defined at particular discrete points along the time axis, not necessarily at every point of time. We will see the meaning of this in a more clear fashion as we go along. So let us talk about a continuous time system. An example of a continuous time system, as an example, let us take this RC network. So we have a source Vs, a voltage source, we have a resistance and a capacitance, and this is the voltage across the capacitor Vc. So we would like to view this as a system in which Vs is the input quantity and the voltage across the capacitor V0 or Vc as the output quantity. So the input-output relation in this case is defined by the following relation. After all, Vs equals Vc plus the voltage across the resistance, and the voltage across the resistance is R times the current to the resistance I, and the current in the resistance is C dVc dt. So R times C dVc dt is the voltage Vs. So if Vc is the output and Vs is the input, there is this differential equation governing the input quantity with the output quantity. So you can put this in a compact fashion as d plus 1 over Rc times Vc equals Vs over Rc, where d is the derivative operator. You can, instead of dVc by dt, you can write this dVc as a more compact notation, which I am sure you are familiar with this notation. D dividing this entire all the terms by Rc, this is what you get, d plus 1 over Rc Vc equals Vs over Rc. So this is a first order differential equation, and this is the input-output relation for this. So this is, you can solve for this depending upon the Vs that you are having, and you can get values of Vc at every instant of time, and the equation itself is defined for every instant of time. This is an example of a continuous time system. As a discrete time system, you have these input-output relations described for discrete values along the time axis. So if this is the time axis, you might be having equations which are valid only at certain points. So the time axis may be defined in units of seconds, microseconds, months, years, as the case may be. For example, I may take this t in years, in which case suppose I graduate this 1, 2, 3, 4, etc. Say this is, break this up, say n, n plus 1, etc. I am interested. I will have an equation which describes the operation of the system at particular points on the time axis. Not, we don't care what happens in between 2 and 3. So that is called discrete time system. As an example, let us consider an organization in which yn is the number of persons in the organization in an establishment, number of persons in an establishment at the beginning of the nth year, at the beginning of the nth year. That is yn. Let me take xn as a number of persons who leave the organization in the nth year, who left the organization, either they retired or left for other jobs or died, whatever the reason might be. Xn is the number of persons who leave the organization in the nth year. Let Wn be the number of persons recruited, new recruits in the nth year. Then you can clearly see that given these variables which describe the operation of the system now we are concerned, the variables are these, we are interested in the number of people employed in the organization. Y of n is the number of persons at the beginning of the nth year. These are the number of persons at the beginning of the previous year. And out of these, x people, xn minus 1 persons have left the organization during that year. Therefore, so many must be less by that amount. But so many people might have been recruited. Therefore, plus Wn plus n minus 1. This is the equation which gives us the number of persons in the organization at the beginning of the nth year in terms of yn minus 1, xn minus 1, and wn minus 1. Let me further assume that the recruitment policy of the organization is such that at the beginning of each year they would like to find the vacancies. Their sanction strength, let us say, is 1000. Therefore, 1000 minus yn is the number of vacancies at the beginning of the nth year. And then they put out an advertisement, recruit people, and then the recruitment policy is such that it takes about a year to recruit people, and therefore whatever recruitment steps have been taken in the nth year will take effect only in the next year. So the number of people recruited in the n plus 1th year is, let us say, this is the target, but all the people who have been recruited may not join, or maybe there may not be suitable candidates. So let us say 80% of this target amount is recruited. So Wn plus 1 is 0.8 times 1000 minus yn. So if you substitute now this expression into this, you can now write yn equals yn minus 1 minus xn minus 1 plus 0.8 times Wn plus 1 is this. So Wn minus 1 is 0.8 times 1000 minus yn minus 1, n minus 2. Because Wn minus 1, this index now is n plus 1 has gone down by 2 steps, therefore this must also go down by 2 steps. That means the persons recruited in the n minus 1th year will be based upon the number of people in position at the beginning of n minus 2 second year. So, if you substitute all this, you have now an equation which will be the previous equation then leads to yn minus yn minus 1 plus 0.8 yn minus 2 equals minus of x n minus 1 plus 800. So, this is an equation which will enable us to calculate the number of persons in the organization at any year n in terms of the values of yn in the previous years, previous 2 years, and also the number of people leaving the organization in the n minus 1th year. So, this can be thought of as a discrete time system in which you have the input xn, the number of people leaving the organization, that is something which is unpredictable. That is the kind of input that you have for the system. So, under the influence of the input, we would like to calculate the output or the resultant is the number of people in the organization in the nth year, yn. So, it can be represented by means of a discrete time system which has got xn as the input and yn as the output. Now, we have to keep in mind that these two quantities, the input and the output xn and yn, have meanings only for integral values of n. So, n is the number of years in our case 0, 1, 2, 3 and so on and so forth. We can't read any meaning in that for non-integral values of n. This has meaning only for n equals 1, 2, 3, 4 and so on. The distance between successive units in our case happens to be years, but in general it could be seconds, minutes or whatever you are having. It is always also conventional that in most of the cases we take these intervals at regular points along the time axis. So, it could be seconds, it could be months, it could be days, it could be years and so on. In our case it happens to be years. So, the point to observe is this is valid only for discrete values of n. And usually they are integral values of n in the appropriate set of units. Now, secondly, this kind of equation is called a difference equation. In contrast to the differential equation that we come across in continuous time systems. In discrete time systems, the equation will be the independent variable takes on discrete values, and the equation of this type is called the difference equation, in contrast to differential equation that we come across for continuous time systems. So, that is the major difference between a continuous time system and a discrete time system. In a continuous time system, you have a differential equation coming into operation. In the discrete time system, you have a difference equation that is important. Secondly, what we would like to know is the order of this difference equation. It is the difference between the highest index and the lowest index. So, n and n minus 2, this is the dependent variable, the difference between these two is 2. So, in our case this is the second order difference equation. In this case, it could be higher orders in a general case. So, in the discrete time system, the points to note are that the equation is valid for specific integral values of the independent variable n, and the independent variable usually is time. That is why this is called discrete time system. But the same methodology is applicable even to situations where the time may not be the independent variable. For example, if you have got along a line, you would like to point out, you would like to graduate this, and you would like to have an equation which specifies the values of some kind of independent variable along discrete points along the line. The space coordinate can also be an independent variable. Even those systems are referred to as discrete time systems because this is a more common type of system. We can say discrete system, but we call it discrete time system even in that case. So the two important differences between a continuous time system and discrete time system are continuous time systems. The differential equation comes into play. Here the difference equation comes into play. And the continuous time system, the variables are described at every point in time along the continuous basis. In the discrete time system, they are defined only for discrete values of the independent variable, which is usually time, and that's why it's called a discrete time system.